Hello, welcome back to another lecture on this sort of building your own operating system series. Yeah, I'm going to carry on from last time. So in the last lecture I talked about well, looking at assembly. So we started to assemble our boot sector, so writing assembly code and then assembling that and then running that inside a machine emulator to simulate what would happen if we booted it on a real machine. So I'm going to carry on from there, and one thing we did, so we looked at interrupts and we looked at how we could instruct BIOS to print a character to the screen by setting a register value with something in the BIOS expected for a teletype printing thing. We'll look at the code in a minute. And anyway, we've got BIOS to print a letter, but what we've not really looked at yet is memory and how that affects our code. So addressing memory, the memory layout of the computer when we first boot, and also limitations of memory in this 16-bit mode. So we're just going to, again, we'll just play around with some code and look at what happens, and we'll use a hex editor to look at the assembled code to see what's in there, and then we'll try and figure out how all this relates to memory. Okay, so let's have a look. So we'll start off with memory. I'm going to start from that last code that I had before, and I'll just summarise what this meant. So we've got 3 lines of assembly here that are used for printing a character to the screen. So if you remember, we used the AX register, which is just a general purpose register in the CPU, and BIOS expected us to use this in a certain way. So first of all, into the lower 8 bits of that register, because these registers are 16 bits wide, running in 16-bit mode, which is a backward compatibility mode of the x86 processor when we boot up. So we load the character H into AL. Actually, our assembler here will be loading the ASCII code for H, whatever that is. I forget, but we can look at the binary in a minute in our hex editor. And then we move this this number OE into the higher 8 bits of the AX register, and this number is just selecting a particular sub-function within the interrupt that we're going to call that is responsible for display functions that BIOS offers to us when we first boot. Now remember, BIOS is just a basic input-output system, and without BIOS we wouldn't know how to communicate with any of the devices at any level, but BIOS gives us a very primitive control and access to the devices like the screen and the keyboard, the disk drives, allowing us to bootstrap our operating system. So we use BIOS there, and then we have an endless jump, and it's always good to put an endless jump at the end of your boot sector, because you don't know what if you let the computer just carry on executing the bytes after your code is finished, then it's just going to be running through random data bytes, executing them as instructions, and we don't want that. Remember, it's us at this low level. It's us that need to we need to guide the CPU. We need to direct it towards our code and away from data. We need to differentiate between what's code and data, because the CPU doesn't do that. So and at the end of here I just have this thing that just pads out my boot sector so that it's 512 bytes long, which is the size of sectors that are read from the disk by BIOS, and on the end of that, so the last 2 bytes of that sector are the magic number that BIOS expects to make it bootable. So that's what we've covered so far, and this was good because we could print an H to the screen, and that's quite a big step at this low level when we've got no support from an operating system or anything else other than BIOS. So now what we're going to do is we're going to try and find a byte in memory and print that to the screen. So we're going to put a character somewhere in memory and print that to the screen, and that's going to help us learn about how we address memory, and also implications about where our code is loaded in memory by BIOS, which is very important. So let's have a look. So we're printing this H here. This is just a literal value. If I look at the if I just compile that, and I look at the hex, then I see this H, this is the H that's being used in that move, so it's moving this value into the register, and the value is 48. So all that's doing, that assembly instruction, is I'll just move this microphone, it keeps falling down. All that instruction is doing is moving the number 48 into the register. And this is our hexadecimal 48, which is the character capital H. And so we don't need to worry about where the H is in memory, because in our instruction we're just moving the literal number into that register. We're not addressing memory in any way. So what I'm going to do now is, if I go back to my code, so I close this. Okay, if I go back to my code, and what I'm going to do now is I'm going to declare some bytes here. So if I do db and then put an X, and then I compile that, and then if I look at the my hex code, now I'll see that when I just put that db, I declared a byte, just a data byte in my code, and I've now got an X in there. So this is my boot sector, this is the raw bytes of my boot sector. Now I want to tell BIOS to print that X, but I've got to tell BIOS where that X is, and to do that I need to understand a bit more about memory. Okay, so let's go back. Well, first we need to know that all the CPU can do is execute instructions that are stored in memory somewhere. And remember that we wrote our boot sector to a disk, to the first sector on the disk, the boot sector, and BIOS loaded that 512 bytes from the disk, and it copied it into memory, somewhere in memory, and then once it had copied it, then it instructed the CPU to start executing the instructions at the first address of the boot sector that was loaded. So my code is now in memory somewhere, but I don't know where it is. Okay, somewhere in my code, at an offset from the start of my code, if I look in my hex again, hex editor, if I look along here, the X is at offset 6, so it's the 0, 1, 2, 3, 4, 5, 6, it's the 6th, so that means it's a 7th byte if 0 was the first. It's a 7th byte inside my boot sector, but that doesn't tell me where it is in memory, it only tells me relative to the start of my boot sector that's loaded into memory, how far into my boot sector that byte is. And if I want to tell BIOS to print it, I need to tell BIOS the address of where it is. So first of all, I'm going to play around with some things. Now, here, I need to move the value of the thing that I want to print into it. So one thing, let's put a label here. So if I put my character, labels are good because we can use them for referencing inside our code. We don't have to keep counting the offsets, but for now I'm just going to play with the offsets that I looked at in the hex, which was mine was offset 6 inside the hex. So what I'm going to do is, for the character in here, I need to tell it to load the character from that address. Now if I put, let me just check that offset again, it was 6, wasn't it? So my X was offset 6. So what I might think that I could do is put OXO6. So what I'm saying here is move 6, so the number 6 into AL, and then I'm going to print it. Let's see what happens. So it doesn't. That's not printed my character. It's not printed my X. It's printed something else in memory, and whatever that is, it's printed an ASCII character that matches the number of the data in the address that it tried to print. Now, in most cases, you'll get a blank character there because there'll be no printable character for that value. Sometimes you'll just get a random character. It doesn't make any sense, but the point is it's printed the wrong piece of memory, so it's not found my X. So my goal of this little exercise is to try and find my X, and then I can understand a bit more about where my boot sector is loaded in memory and how to address data. So we'll close that down, have another look. So that didn't work. Now, one thing we should have done anyway is this is loading. This is actually loading the number 6 into the register. So this will be printing the ASCII character OX06. So let's just look on an ASCII table. See what that is. See this on website. So we were in hexadecimal. Yeah, it was a non-printable character that I printed. So it just printed some random thing. Anyway, let's go back. So remember, what I'm trying to do is find that X. If I can find the X, then I'll understand more about how to address memory. Well, the first thing I need to do is not move. I don't want to move a number into this register to print, because this will be the ASCII character value that wants to be printed. What I want to do is use this notation in my assembler. If I use square brackets, then it means don't put that value into the register, but go to that address and load the data at that address into the value. So I'm addressing it. I'm not loading the literal value in. I'm saying here's an address. Go to that address in memory. So this is now that this is the first time I'm really accessing memory, and it's saying move the 6th byte in memory into this AL register. You can think of memory as just a long sequence of bytes, and we can index those by just so the first byte in memory, so the very lowest byte in memory is 0. We can access that at 0. The next one will be 1, 2, 3, 4, and we can just access memory like that. So that's what I'm doing when I put this thing in brackets. So it's telling my CPU to go off and find that whatever's in there. Okay, well, let's try this anyway. So now all I've done is, rather than just putting 6 in there, I've said get me the data that's stored in address 6 in memory, and store that in AL, and that's going to be the character we want BIOS to print. So let's see what happens now. Okay, it printed nothing. So again, we've not got what we want yet. So what was that then? Let's think about it. So you might have remembered that I think I might have said when BIOS first loaded us that there's already stuff in memory, so BIOS is loaded into memory. So that's one of the first things that happens. BIOS code is copied from its chip into memory, and then it starts to execute. And it's only after it's executed that it will then start to look for the drives, and it will look for the boot sectors with the magic numbers and load them into memory, and then finally pass execution to those boot sectors, and that's how an operating system boots. But there's actually that 6th byte at the start of memory, that's actually somewhere in the interrupt table that BIOS set up. So this is not my boot sector, so my X is not going to be in that interrupt table, my X will be somewhere else. So what we could do at this point is we could I could keep editing my code and compiling it and increasing that character until I saw an X. And once I found that X, I could put some other character in, like a Y next to the X, and I could see that the Y is next to it, just to make sure that that's my X and not some other X that was in memory. And what I'd find is that if I put this value in, so address 7C06, let's see if this works. That one didn't work, so now what I've got to do is check my offset again, because every time I edit my code, and so there I've added another 2 bytes to the address, it's going to push the index of my X down. It was in character 6 before, but if I look at my hex code again, I'll see that my X is now at offset 7. Okay, so by changing that opcode, the address in that opcode, it's pushed my X along. So let's close it. So now all I need to do here is say 07. Oh, there's my X. Okay, this is good, okay. But what does that mean then? What it means is that my X is stored at the memory address, so the absolute address in memory, at 7C07. Now, when I looked at my my binary code that I compiled, I saw that the X character was at offset 7 from my boot sector code. So what that means is that BIOS loaded us to address 7C00. This address. That's where BIOS loaded us to. Now, if I look, I've got a little diagram here that explains, that just gives a simplified layout of the low memory when the computer starts. And BIOS always loads us at this address, so this is a well-known address where our boot sector code will be loaded. And you might assume at first, if you didn't really think about it too much, that BIOS would just load you at the start of memory, but you can't make that assumption. In fact, the interrupt table is there, and we're going to have to play around with that in a minute, well, at the end probably, just to confirm that that's there. And then there's some other BIOS data area that BIOS will be using, because BIOS has got its own code in memory, and it's got its own data that it uses in memory. And then there's this big gap of free space here from 500 all the way up to 9FC00, and the boot sector gets loaded here, so 512 bytes from 7C00. So that means on this diagram our X would be somewhere in here. And so if we want to print that X, we want to tell BIOS to print it, we have to tell the BIOS code that is going to run when we fire our interrupt to look at that address. So in our case it was 7C07, the X was. So it's important to know where BIOS loaded is in memory. Right, so what can we do then? Well, if I go back to my code, the first thing is that when I was wanting to print this X to the screen, and I was looking in to find its offset, so here it was offset 7 from my code, I was looking in my hex editor, and the whole reason we used an assembler NASM instead of using a hex editor was because we didn't want to be doing things like that. We don't want to be manually calculating offsets every time we change our code, because that X, when I changed the instruction to add a new address into it, that X was pushed down an extra byte in our code, and I had to then check in the binary file to see that it had moved from 6 to 7. Anyway, we don't want to be faffing around with that kind of addressing, so we want to use labels. Now, what we can do, well, first of all, I did demonstrate this before, but what we want to be doing is something like this. Because remember that these labels in the assembler, once it's all been assembled, these will resolve to the offset of that instruction. So in this case, it's going to resolve to the offset of this X, which is good. So if I add any more lines here, any more instructions here, this will always resolve to this offset. Okay, it's exactly the same with when you have C code and you declare a function. When it all gets compiled down, that function ultimately will just become an address that gets called, that gets jumped to execute the function. Remember, the computer doesn't know about labels, and this is just something that we use as a convenience for defining offsets within our code. Anyway, we want to be able to write something like this, where we can say, take the address of my character and load the data stored in it into the AL register, and then call BIOS to print it. That's what we want. But if I do this, this is similar to what I did before actually, but now I'm using the label instead of the offset. But if we do this, we'll see that it doesn't print it properly. It prints the wrong thing. There you go, that's not RX. But what we can do is, in our assembler, if we put this OX7C00, then this tells our assembler that this code is going to be when we're talking about addresses relative to the start of this code, like labels, this label here, it's going to say to convert that into an absolute address in our binary file once we've assembled it. Treat this as the origin of our code. So we know that BIOS is going to load us to this address, so if we stick this line of code in our assembler, then the assembler will always know how to calculate our labels into the absolute addresses in memory of where they'll be once it's loaded into memory. Okay. So if I now run this code, there's our X. Okay, and just to because that X could be somewhere else in memory, so it's useful to do things like this. Let's call that my character 2, and we'll put a Y in there. So if I just copy those lines, actually I don't need to copy that one because it's already in the AX register, and if I put my character 2, now we should see it print an X and a Y. Let's see. There we go, we've got an X and a Y. So we can be fairly sure that we are printing our X and Y's that are within the range of our boot sector and not somebody else's. So that's important. Okay, so now we know that BIOS loads us to that particular address in memory, and knowing that, we can then instruct our assembler about how to calculate our label offsets, so they can work with data that's stored within our boot sector. So the kind of data that I might want to store in there are strings to print out, or things to search for in memory, anything like that. I suppose it's the equivalent in C of having constants and things like that. So now we can access data, so that's good. Now if we go back to here, one thing, this is where it gets a little bit confusing, and that's widely acknowledged, but we're in 16-bit mode now, so our registers hold 16 bits, and which is 2 bytes. So if I want to access somewhere in memory, so if I look at my code now, luckily my character, like let me get rid of this again now, this org thing, and use the absolute value that it was at. Let's get rid of this one and this one. So if I do this, my character, so rather than using that offset, let's just pretend that we're just doing we're just going to put the absolute addressing that we know, because we know BIOS loaded us there and we calculated it. So there's our X. Now, AL, we can't move. We tried this in the last lecture. If I wanted to put a larger address into this AL register, I mean, if I wanted to use a larger address here, I couldn't do that because the processor is running in 16-bit mode. This is the maximum address that I could put into here would be, that's the biggest address. Okay, so that means that if we've only got 16 bits of addressing, then we're very limited to the memory we can address. So that would be 2 to the 16. If we look on here, it's quite an interesting page. So we can see that if we've got 16 bits, we can work out how many bytes we can address in memory, and the maximum is about 64 kilobytes, roughly 64 kilobytes. That's not a lot of memory if you think that you've got gigabytes of memory in your machine. What it means is that in this 16-bit mode, using addresses like we are doing, we can't access very much memory, which is partly when memory was very small anyway, when computers, and programs are very small. Probably programs are mostly written in assembly as well and did very specific tasks, maybe doing calculations and stuff. Then that was probably a lot of memory. But anyway, we've got a memory limit there. So the question is, in this 16-bit mode, how can we access more memory than 64 kilobytes? So there's this idea of segments, okay, and this is a little bit confusing, and it's been superseded in when we look later on at 32-bit mode. It becomes memory, accessing memory, extended memory, becomes a bit more sensible. But these segments, this idea of segments, allows us to access more memory in this 16-bit mode, but it can be a little bit confusing. I mean, it's a bit strange how it works, so let me just explain that and we'll look at some examples. Okay, so if we go back to my code, so we know that our byte is here, and 7C07. So this should print my character. Yeah, there's my character. That's good. So I'm going to look at segments. So, well, how this works is, if I go to this OSDEV site is very good for information on the CPU and how you can start to write your own operating system. So they've got interesting pages that kind of try and summarise the main Intel documentation, just to make it easy to digest some of this stuff, how it works. But the way segments works is that when I access an address, when I put that address in my code, so when I put this 7C07 address in my code, that's not actually that doesn't map directly to the address in memory that byte comes from. The CPU looks in special segment registers that I can change, and if, well, it takes those the values in those segment registers, and it uses those and this address here to calculate the absolute address. And what that means is that by changing the segment registers, it will change the absolute address that this accesses, and basically by increasing the value in the segment register, it will increase the range of this local address. But it's a bit strange how it works. So there's a simple calculation for it, but it's just it's a bit fiddly for programming in to access extra memory, and that's why in 32-bit protected mode it was simplified to make it more sane. And in fact, we probably won't need to worry about this too much, because what we'll try and do is switch into 32-bit mode as soon as we can, which is what all modern operating systems do, or into 64-bit mode. It's very similar. We'll switch into that as soon as we can, so we don't need to worry about this horrible stuff. So, how does it work? Well, it just takes, there were these registers, so like AX and BX and CX and DX, they were all general purpose registers, and I said that some registers are special purpose, so they have if you store a value in there, it will affect the CPU, how it works. It will effectively change the state of the CPU, so it does something different. Now we have these registers, the CS, DS, SS, ES, FS and GS. We don't need to worry about these ones, these last four, because some of them are just like optional ones that you can use if you want to, and we'll talk about the stack later on. But we've got the code segment and the data segment. And the code segment affects how, when the CPU is executing instructions, how the address for the next instruction is calculated, based on something that you've stored in the CS register. DS is the same but for data. So in this case, when I'm trying to access my X, the CPU will be checking this data segment and using that and the address that I typed in here, this 7C07, to calculate the offset in memory, the absolute offset in memory. And it does it like this. So to work out this physical address, the actual address that it accesses, it takes the value in the segment. So for my X, because it's data that I'm accessing, it's going to take the DS, the value stored in the DS register, multiply it by 10 in hexadecimal, and then it's going to add the value that I've put into my code, so that's 16-bit address value. So let's have a look at this. Let's have a little play to see if we can demonstrate how that's working. So when I move this value into here, I'm assuming that the data segment register is 0 and it's adding 0, and that's why this is printing the X, because this is the absolute, this is the physical address in memory that it's going to access. Now if I put if I try and move a value into the data segment, and what I'm going to do is try and make it so that I can just put 7, so I can use like a local offset to my X in there, and I'm going to try and set up the data segment register so the start of the segment is going to align with the boot sector that gets loaded at 7C00. Well, what can I move into there? Let's see. If I put OX 7C0 into there. Now I'm doing something here to show you. We're going to get a mistake. It says invalid combination of opcode and operands. So why is that? We've got this data segment register, and I want to move this value into it to set up a segment to make it so I can reach further into memory if I wanted to. But it's saying I can't do that. Although I can move values into my AX registers like that. But what you find in assembly is that what things look like when you write the code is not always how the computer works underneath. And what I have to do in this case is I have to first move this value into a general purpose register. So let's say BX, and then I have to move it from one of these general purpose registers into my segment register, and that is just because the CPU won't let me do it directly. Won't let me set a value directly in a data segment register. I have to do it via another general purpose register. So I will summarise this stuff as well. I'm really trying to, I suppose I'm just trying to demonstrate, for example, how this works, and then I'll go over it again. I'll explain it again. So we're going to move whatever's in BX into DS, and we'll see that it should allow us to do this. It did do, yes. It didn't print an X, but it let us do that. So I've set the data segment now to point to this, and I've set my offset to 7. Now what I'll find is, because I've added these extra assembly instructions, it's pushed the offset of my X down. So if I look inside my my hex code, if I look in the hex, I see that now it's at OXC. Here, look, the offset of my X. So let's go back and look at the code. And that means that what I need to do is put a C in here. Now let's see if this works. Hey, there's our X. So what happened there then? What have we done? Well, first of all, I took that org thing out. So my assembler doesn't know where BIOS loaded us to. It doesn't know how to calculate the absolute addresses for my labels. I took that out because I wanted to show something different. I wanted to use absolute memory addresses to show how the segmentation worked. So rather than accessing it with the label, I was using the local offset to access it, which is C in this case. So it's the C, so that would be so A, 10, 11, 12. So that would be the 12th byte in decimal into the boot sector is where my X is. So I'm now saying load 12 as the address into AL. So the value stored at address 12 into the AL register, and then call BIOS to print it, and that's going to print my X. Now we know, because I just mentioned before, that because BIOS loaded us at 7C00, my X is not stored in the 12th byte in memory. That's the interrupt table somewhere in there. So I was demonstrating that by changing the data segment register, I can affect how these addresses that I write in my code are translated into physical addresses. And in this case, I manipulated it so that I put this value 7C0 into the data segment, and then when I did access this, it then became using this computation to work out the physical address, it was the data segment, what was in there, times 10 plus b. So what that is so this is going to be OX7C0 times by OX10. Now when we times it by 10, it's in hexadecimal, it's the same as shifting it. We can imagine shifting it to 4 bits to the left, so that then becomes OX7C00. Yep. And then what I do is I take that and I add OXC to it, and that becomes it becomes OX7C0C, which is where our byte is going to be stored in absolute memory, because we know it's the C offset, 12 byte offset, from the start of, from where our boot sets were loading in memory, which is 7C00, and that's where it is. So we showed there that how this segmentation works. Now in my case, I didn't really need to set the segment up, because I could access by putting 7C0C as the address that I load into here. I could easily reach far enough into memory to get my X. But if you look at this, diagram here, then look at these addresses up here. For example, video memory, which we'll be using later on, is another way to allow it to display things on the screen. And it's at this address here, A0000, and it's larger than 16 bits, that address. So it's, that's 20 bits long, that address. So to use that, I need some other way of changing the segments to reach that memory. I need some way of accessing that memory, and if I can only specify memories as 16-bit values, then I need to set the segment up so that the segment will be set up somewhere close to this, and then I can reach into that memory. Now we don't, for much of what we're going to do, we don't need to worry too much about this 16-bit real mode segment-based addressing. It gets much simpler when we come to work in 32-bit mode, but it's good to know that. You need to understand, firstly, that it's a bit weird how it works. It's a bit strange shifting an address by 4 bits in the segment and then adding your offset address to that. It's a strange way of calculating physical memory, but I suppose when the CPU was developed, that was a way of accessing more memory, but with a 16-bit architecture. So that's how it works. So that's very good. Now, so we've covered the most important parts of memory, really, and I'm going to just look at playing with the interrupt table just to demonstrate that the interrupt table is loaded down there at the start of memory, from the very first byte in memory. So we don't need to worry too much about that 16-bit segmented based addressing, but you just need to know that it exists. Okay, right, let's have a look. Let's have a play with this smashing interrupt table. Now remember, the best thing for me to do now is to just forget all of that absolute memory addresses and stuff like that, and let the assembler help me. So I'm going to put this stuff back in. So 7C00, that's the origin of where we get loaded in memory. I don't want to be putting absolute addresses to reference things. I want to be using labels and let the assembler calculate those. Now let's just check this is working before we carry on. Yeah, so there's my X. So we're back to where we were now. Now what I want to do is I want to show you that you've got a great power working at this low level. You can write to any area of memory, and if you do it by mistake, then you're probably going to break something. you have to be very careful about controlling the flow of your code, so that you don't let the CPU start trying to execute data, at least if you don't intend to. Otherwise, you've lost control of the CPU. It's going to carry on processing that data as though it's code, and you'll never get control back over it again until you reboot the machine. So we've got to be careful. But we're working with an emulator. We're just playing around here. So let's just see if we can corrupt something, and in a way that will teach us something. So we're loaded up here, our boot sector, and I said that BIOS was loaded first. BIOS loaded its own code, and I think the BIOS code is probably up here, and there's some BIOS data down here. And at the very start of memory, we've got the interrupt vector table. And if you remember last time, I talked about, in the last lecture, I said how this BIOS thing works. So we set up our sort of arguments for BIOS in the AX register, so the character we want to print, and the particular BIOS function for displaying a character that we wanted. And in this case, we wanted the teletype function, which just meant that it printed one character after another. And I said before, there are other functions that let you print to a particular place on the screen and stuff like that. And then we call this interrupt 10, which is 10 in hexadecimal. And this, what I said this did, it switched, it caused the CPU to enter into an interrupt state, where it looked in an interrupt table that was set up, which is just a table that links interrupt numbers, in this case the number 10, to an interrupt handler, or an interrupt service routine, an ISR, and it executes that code. And in this case, BIOS had set up its handler for printing stuff to the screen to help me print stuff, and that's what was happening when we did that. One thing I don't think I did mention was that there are two ways to create interrupts. Software can create an interrupt, and hardware can. So software usually creates interrupts to to do things like this, and hardware creates interrupts when it's finished doing things usually, or if there's an event that needs processing. So the disk, we'll look at the disk later on, but for example I might tell the disk to read a sector later on, and because it does that far more slowly than my CPU can execute code, then I don't want to wait for it to happen. So what I do is I'll in my operating system, when I set it up, I'll have a handler for a particular interrupt that the driver, that the disk is using, and I'll just tell the disk to read a byte, and then I'll carry on doing what I'm doing. And when the disk is finished, it will signal that interrupt, and my handler code that I register for my disk driver will then it will then process that data that's been copied to memory or something like that. So I'm not waiting for things, I use interrupts. So software can create interrupts like I'm doing here to interrupt into BIOS, and hardware can do the same to have handlers called. It's the same principle really. So that's our interrupt. So what I want to show now is that interrupt, the BIOS set up that handler for printing that X to the screen, for printing my character to the screen when I call interrupt 10. And if I corrupt the interrupt table in a particular place, then I should be able to stop it printing my X. So I'll keep my code as it is here, but I'm going to corrupt the table and then see if my interrupt still prints an X. And if I can corrupt the table, then it means that BIOS will then be unusable for printing to the screen. And but it also demonstrates that the interrupt vector is at the start of the memory. So I'm going to change a byte somewhere in here, and then call an interrupt, and it's going to not work. And that's the plan. So first of all, we'll start off with being a bit naive, but let's just check. So I run this again, and I get an X. Okay, that's good. So BIOS is printing the X for me. I'm telling it to do that. Now I know that BIOS is it set up the interrupt table at the start of memory, and if I move a value to let's say 10, so I'm going to say move to 10 0. So what I'm saying is, I'm using these square brackets again, so now what I'm saying is the address in memory that's hexadecimal 10, so it's the 10th in hexadecimal index into memory. So that will be somewhere in the interrupt vector table. Move a value 0. Now in this case I have to put this here. I'll just explain this. In fact, I'll leave it out first and then you'll see an error message. But what I want to do is move the value 0 into the this offset in memory, so into the interrupt vector table, table. And I'm doing that because I want to overwrite something that BIOS set up in there. And if I overwrite it with a 0, it's likely going to break it, because BIOS would have had an address of something, of the handler for that interrupt, or it might be, some other information in that record. And if I overwrite it, then it should break it. Let's just see what happens when I do this. Okay, so it's saying operation size not specified. So what I've got to do is if I put word in here, then it works, but it still prints an X. Now first of all, why did I have to put word in there? Now the thing is, if this was a register and I did move, say BX OX0, it wouldn't complain because it knows that BX is 16 bits wide, so it'll convert this value into, it'll essentially be this, like this. Okay, and it's going to move that value into there, and then well, it knows it's 16 bit wide, so it doesn't complain. But in this case, I'm taking this value 0 and I'm moving it into this position here, and it doesn't know. That's just an address in memory. It could be, I could be wanting to write a single byte, or I could be wanting to write 16 bits, 2 bytes. It doesn't know what I want to do there, so I have to tell it word. And this will then get converted by the assembler into the right opcodes for moving 16 bits as opposed to a single character. That's all. So I have to put that in there. So does this corrupt BIOS? Well, we saw that it didn't do. Look, we still get the X there. Okay. So let's have a look. We need to understand how the layout of the table is. My assumption there was that the 10th interrupt 10 in the table was at the 10th byte in hexadecimal in the interrupt vector table, but it's not actually there, because it turns out that in the interrupt table, for each record, it has 4 bytes. Okay, 2 16-bit values. Now, if I go to this page here, there's a good page on this. If I go to the interrupt vector table here. Okay, so here this is for each record in interrupt vector table, we've basically got a segment and offset, which is it just allows us to access a handler in memory somewhere, but it uses 2 bytes. But it still means that the first interrupt, so interrupt 0, would be the first 4 bytes of the interrupt vector table. The second interrupt, so interrupt 1, would be the next 4 bytes in memory. So what that means, if I want to corrupt, where is it gone? If I want to corrupt interrupt 10, so the 10th entry in the interrupt table, so that it no longer maps to the BIOS display functions, then I want to multiply this by 4, and that should hit it. And I'm going to overwrite it with zeros. Ah, there we go. It no longer prints an X. So it can't. There's no link now from the interrupt 10 to the BIOS code, because I just overwrote it in the table. So this is good, because we can see that, what damage we can cause at this level, but also we can appreciate how BIOS is working. There's no magic. There's no real magic. It's all working in the same way. The BIOS code was loaded in memory just like mine is, and it's running in memory. And like I said in the earlier lecture, if I wanted to copy all the bytes out of that memory and then disassemble it, I could look at the BIOS code to see, what does the BIOS code look like. It's just that BIOS did all of that setup initially to, map handlers for the disk drive, so that I could use the, so we could use the disk to load stuff we can print to the screen. But it's just code in memory, just like my code is, and I can change its code, and it could change my code if it wanted to. And here I just corrupted it by writing to the entry, the 10th interrupt entry in that table, so it no longer mapped to a handler. So there we go. That's everything really. So what were the main important things that we learned? We learned about memory, that memory is just a sequence of bytes, and we can index them with addresses. One important thing was we saw that if we used the square brackets, if we used these square brackets like this, it meant load not the value, like this offset in this case, into the register, but the value at the address in memory into that register. And this relates very closely to C pointers, which we'll look at later on when we look at writing C code. And then we looked at the limitations of using 16-bit addresses and how using segments in the x86 architecture we can access more memory. And then at the end we just demonstrate the power of, that we have over the computer at a slow level, and also just to show that BIOS is actually relying on a piece of memory for the interrupt table to allow us to use BIOS. We showed that we could just corrupt that table and then stop the BIOS stuff from working. So there we go. In the next lecture we'll look at the stack, and we'll start to look at how we can call functions. Or there are no real functions in assembly, but we'll look at how we can create a function like behavior, which is how functions are abstracted at higher level languages. The CPU doesn't know what a function is, but we use certain functions to help us to build functions. We use certain CPU operations to help us to build them. Yeah, I think that's it really. So memory. So there you go. We'll start to use this stuff, and then it will become clearer as we use it, if it's not clear at this stage. But I hope it was interesting. Thank you.